there is a very serious question about what is waving in this case. We remember that for photons, we knew that what was waving was the electric field. And we knew that the probability of detecting a photon somewhere was proportional to that electric field squared. Now, when it comes to what's doing the waving for a particle, like an electron, we don't really know. But we say it has a wave function, psi, it's Greek letter psi, and we say the probability of detecting the electron at any place is proportional to that wave function squared. So somehow or another, whatever's waving is the square root of a probability. In some ways, that's a very unsatisfactory answer, but in reality, we've never found a way to measure this wave function directly. We can measure the wave function squared by measuring probabilities, and we can measure interference between waves, but we can't make a direct measurement of the wave function. Let's talk a little more about the wave and particle nature of an electron. We've been told that the wave is described by a wave function psi, and the probability of detecting an electron is proportional to that wave function squared. But I can set up a detector that basically detects the electron continuously. This is a picture from a bubble chamber, and an X-ray has come in here, knocked an electron out of an atom that goes very fast, and also decayed into an electron and a positron, both of which are spiraling off to the sides. Clearly, these are traveling in well-defined paths, just like a particle would. They're not acting like a wave. But remember, we said when we were discussing the photon that the photon behaved like a wave when we weren't detecting it, and like a particle when we did make a detection of it. So essentially what's happening in that bubble chamber is that we are constantly detecting the position of the electron. By constantly detecting its position, we are forcing it to behave in a particle-like manner. We can also understand this from a slightly more wave-oriented picture. This is a picture developed by Richard Feynman. But we can imagine that that electron wave propagates out from the initial to the final point in all directions. Each one of these paths has a different length, and therefore picks up a slightly different phase in the wave. However, the shortest path is only very slightly different in phase from the path that goes right above it. And it's only very slightly different in phase from the path that goes right beneath it. As a result, this straight line path adds constructively with its nearest neighbors and becomes the dominant effect, the most likely path, the highest probability. By contrast, paths such as this curved one here are very different from the path just below it, which is noticeably shorter, and the path just above it, which is quite noticeably longer. As a result, we get predominantly destructive interference for these paths that are not the straight line. So we can, in fact, describe the path taken by a particle in terms of its wave. It's the straight line path because that's the path where the phases of adjacent paths add up constructively.